4.5 billion year old planet, still evolving. As continents shift and clash, volcanoes erupt, and glaciers grow and recede. The Earth's crust is carved in countless fascinating ways, leaving a trail of geological mysteries behind. This episode investigates one awesome force that shapes the Earth. It's extraterrestrial, and it doesn't happen over millions of years, but in seconds. It's a force caused by an immense impact from asteroids, giant rocks from space. The investigation of asteroid strikes has given scientists insight into the formation of the universe, providing a window into planet Earth's ancient past. There is a giant hole in the Arizona desert, 35 miles east of Flagstaff. It's huge, 3/4 of a mile wide and 550 feet deep. The Washington Monument could fit inside it. The mystery confronting geologists in the late 19th century was, how did this happen? People agreed that only a massive force could have created such a huge chasm. But what was this force? The most likely theory was that a huge volcanic explosion had ruptured the rugged landscape. Scientists had discovered similar-sized craters in volcanic areas before. But Grove Gilbert, chief geologist for the U.S. Geological Survey, had another idea, one that came to him after observing craters on the moon through his telescope. He saw similarities between the moon's craters and the mysterious hole in the Arizona desert, leading him to speculate that the Arizona crater might have been caused by an asteroid impact. But this was just a theory. At the time, no one had proven that any crater on Earth had been caused by an asteroid. So in 1892, Gilbert decided to travel to the mysterious Arizona crater.
He wondered if this could have an impact origin or alternatively a volcanic origin. And so he had these two competing hypotheses that he wanted to test.
Gilbert assumed that if the crater was caused by an asteroid, he should find a giant alien rock in the middle of it. But there was none. But he did see what he thought were signs that a volcano might be the cause.
When Gilbert arrived, he realized that this hole in the ground was associated with some volcanic peaks in the distance. You can see them in the background over the rim or beyond the rim of the crater. And so immediately, I think he was prejudiced, if you will, towards a volcanic as opposed to a meteoritic origin.
Not far from the mysterious crater, Gilbert found another similar giant hole. He declared this one as an unusual volcanic crater called a maar. He knew that 4 years before in Japan, scientists had witnessed the formation of a maar after a huge underground explosion of steam. The resulting crater resembled the giant hole Gilbert came across in the Arizona desert.
They are produced when basaltic magma rises through the Earth's crust, encounters groundwater, creating a steam explosion which causes a blast that produces craters like the one over my shoulder.
Intriguingly, the two almost identical craters were only 50 miles apart in the same desert. One was known to have been caused by an underground steam explosion. Because of their close proximity, Gilbert concluded that the mysterious crater was also caused by volcanic activity. In 1896, he published his findings in an influential report, and for the wider geological community, the debate was resolved. But 6 years after Gilbert's findings, American entrepreneur and mining engineer Daniel Barringer arrived on the same scene. He was intrigued by mysterious small iron rocks shepherds had found around the crater while grazing their herds. Barringer was convinced that Gilbert was wrong about the crater's origins.
I'm holding in my hands a fragment of what started it all. It is not the type of material that one finds in any other geologic terrain or created by any terrestrial geologic process.
Iron in rock is usually mixed with other minerals, but at the mysterious crater, the iron was almost pure. And there were large amounts normally not found on the Earth's surface, spread over a huge area surrounding the crater. Barringer believed the pieces found here were meteorites, small space rocks that form when big asteroids break apart. He had a hunch that this huge hole in the desert was formed by a giant asteroid made largely from iron. Barringer immediately saw the commercial opportunities. From the crater's size, he calculated that the asteroid must have weighed 10 million tons. With iron then at $80 a ton, Barringer was convinced he could become a rich man from mining the iron. So in 1903, Barringer bought the crater site of over 1,200 acres and hired crews to begin digging. Convinced it was an impact site, he named it Meteor Crater.
We're in one of the remnants of Barringer's mining camp. This is a place where his miners lived, ate, slept, while they looked for the buried meteoritic mass that they thought was beneath the floor of the crater.
For years, Barringer and his men found only small fragments of iron. Undeterred by this, they kept digging deeper shafts into the earth.
The largest of which, the main shaft, you can see is a white island of debris in the center of the crater. And in fact, one of those holes, close to me here, reached a depth of nearly 1,400 feet beneath the surface of the Earth. In all of these cases, or most of these cases, they found telltale hints of the impacting meteoritic body, but no giant mass.
Barringer did stumble across some clues, however. Strange and unique rock formations, such as fine pulverized rock spread around the crater.
He noticed, quite rightly, that it is so fine it is almost like talcum powder, the type of thing that immediately alerted him to something unusual in the geologic processes that shaped the land here.
To Barringer, the pulverized rock was a major clue that pointed to one thing: the violent impact of an asteroid.
As a geologist, if I saw this rock, I would say, okay, this is not something that I see around a volcanic crater. There's something going on here, and I need to figure it out.
Barringer also discovered other oddities. At the crater rim, he noted a bed of rocks that were chaotically overturned.
Dramatic energy uplifted the rocks in the crater wall behind me. Originally, they were absolutely horizontal, and you can see that they are tilted upwards. And if you look very closely at the very top of the rim, they are completely overturned.
For 27 years, Daniel Barringer obsessively sunk mining shafts in search of his giant iron asteroid, with no success. Barringer died in 1929, having lost $600,000 of his own and investors' money. $10 million in today's dollars. The privately owned crater has remained in his family to this day. But his theory about the asteroid impact at Meteor Crater spurred further investigation based on 3 clues he had uncovered. The first, the pieces of pure iron scattered across the crater. Next, rock that had been crushed into fine powder. And finally, strange rocks thrown up and flipped over at the crater's rim.
Interestingly, even though Barringer hadn't convinced the geologic community about the impact origin of this crater, he had launched at least a small number of people into an investigation of impact processes.
Proof of Barringer's asteroid theory would get a boost, some 6 decades later, from an unexpected source. Meteor Crater in the Arizona desert was still a mystery to the geological community. The debate on whether it was caused by volcanic activity or an asteroid impact wasn't resolved until 1960. a young geologist, Eugene Shoemaker, became interested in Barringer's research. He would take the investigation in a new direction, which turned Meteor Crater into one of the most investigated crater sites on Earth. Shoemaker was working on craters left by nuclear explosions on test sites in Nevada. His task was to find out how the explosions transformed the landscape. Intriguingly, at the test sites, he found the exact same rock formations Barringer had described at the mysterious Meteor Crater in Arizona. Shoemaker passed away in 1997, but his wife, astronomer Carolyn Shoemaker, recalls his findings.
Gene compared Meteor Crater with the craters that he had been mapping at the Nevada test site. At the test site, Gene saw overturned beds also near the top of the craters in the rims, and that certainly told him that there was a strong similarity because they were so obvious at Meteor Crater.
Shoemaker came upon another important clue that linked the Nevada test sites to Meteor Crater.
He found samples of this very unusual rock. This was once sandstone, but he recognized it had been altered.
In the craters left by explosions from nuclear bomb testing, Shoemaker discovered crystalline structures, the same structures found at Arizona's Meteor Crater.
Today we understand that this is shocked sandstone glass. That is, the original sandstone, all of the quartz crystals were melted and put into a frothy, bubbly, glassy matrix, which we have here.
They were caused by the incredible energy released in the shock waves of a nuclear blast. For Shoemaker, it was conclusive proof that the vast Meteor Crater wasn't formed by volcanic eruptions. Instead, it was created by a powerful asteroid impact in just a split second. The shocked rock also gave scientists a clue about the age of the crater. When an asteroid hits the Earth, the energy from the blast is absorbed by the surrounding rock. Using a process called thermoluminescence dating, scientists are able to measure the amount of energy the rock is giving off in the form of light. The shocked rock from Meteor Crater told them that the impact happened 50,000 years ago. But for some, there remained one problem with this theory. If the Arizona Earth was crushed by a huge asteroid, where was the rock that made the impact? Scientists had a hunch that when it struck, the iron meteorite had vaporized. Conclusive evidence came in 1997, when scientists were able to simulate the impact using advanced computer modeling. From the size of the crater, they calculated that the asteroid must have weighed at least 300,000 tons when it struck. The data further revealed that it hit Earth at a speed of over 25,000 miles per hour. That's 35 times the speed of sound. Upon impact, the asteroid triggered a massive shock wave, many times more powerful than a nuclear explosion.
Within a matter of seconds, this impact crater behind me was excavated and this debris was deposited on the landscape. Within seconds, the shock wave and the very high velocity air blast radiated across the landscape.
The shock wave traveled back up through the asteroid's iron core, vaporizing most of it, and scattering the rest in small pieces over a wide area up to 6 miles away.
The energy that produced this crater ranges somewhere from a few hundred to perhaps 1,000 times greater than the energy that destroyed the cities of Hiroshima and Nagasaki in World War II.
The investigation has uncovered reasons why there are no big remnants of asteroid rock in the Arizona crater. Crystalline structures in the rock showed evidence of a strong shock wave that followed the impact. Computer modeling revealed that the speed and size of the asteroid created enough energy for the rock to vaporize when it hit.
This crater is particularly important because it is the youngest and most pristine impact crater on the surface of the Earth. It was also the first recognized impact crater on the surface of the Earth, and so it is in some sense the Rosetta Stone. It is the touchstone for geology. It is here that specialists from around the world come to study and learn about impact cratering as a geologic process.
Since 1960, when Shoemaker proved that Meteor Crater was an impact site, geologists went looking for more. Armed with this new information and the developments in space and satellite technology, they would revolutionize our understanding of how asteroids have shaped the surface of the Earth. Once the Meteor Crater in Arizona proved an iron mass can burst from space and create a monster chasm, scientists began to search for others. They questioned whether some craters they thought of as volcanic were in fact caused by asteroids. The investigation turned to Sudbury in Ontario, Canada. There is no obvious crater, but for over 150 years, the city has been the center of fabulous mining wealth and a geological mystery. 3,000 feet below ground in one of Sudbury's mines, thick veins of copper and nickel are on view. Until recently, these mining riches were associated with volcanic activity.
One of the really distinctive features of Sudbury is the fact that it has world-class metal deposits associated with it. And originally these were thought to be related to volcano activity, volcanic activity, and magmas coming from inside the Earth, bringing ore and metals from the inside out.
But something didn't add up. When scientists investigated the rocks around the mine, they were surprised. None of the outcrops were typical of the types of rock created by a volcano. To geologists, it was a hint that the copper and nickel treasures below the surface were formed by a different process. They were stumped until they came across Eugene Shoemaker's work on Meteor Crater. It made them wonder whether this vast mine could also have been formed by an asteroid impact. Could the vast reserves of copper and nickel have arrived from space? Rocks above ground reveal new evidence.
What we have is a conical type fracture system with these lineations or lines running through them, and they focus down into a point.
These deformed rocks are called shatter cones. Spray is convinced that the only force powerful enough to deform a rock into a shatter cone like this would be an asteroid impact.
And these are formed due to the shock wave interacting with the target rocks. And they compress the rocks just like compressing a spring, and then when the shock wave releases, they form these conical-like structures, which are beautifully shown here. So these are diagnostic of impact. We can't form them any other way. You can't form them with dynamite. You can't even form them with nuclear weapons.
But shatter cones were only a hunch. Another clue came from the composition of the rock. It's a mixture of violently broken pieces fused into melted material.
So what we have here is made up of the debris from the Earth's crust, blasted into millions of pieces, and the darker core material may well contain traces of the meteorite left in it in the form of iridium.
Iridium is one of the rarest metals on the surface of the Earth. In space, it is 1,000 times more abundant. Asteroids are like space rubble, and their composition varies dramatically. Some are made of rock-like material, some from metals such as iron. But they all have one thing in common. They all contain comparatively large amounts of iridium. So any high amounts of iridium found on Earth becomes a fingerprint of an impact event.
So what we're going to do is take a sample and analyze it to see if we can find an enriched iridium signature, which would tell us that we have a particular class of meteorite.
To find iridium, the lab samples of the crushed rock are heated in a furnace to over 1,000 degrees Celsius. The rock melts, and metals in the rock separate out and form a disk. When the disk cools, it is analyzed for traces of iridium.
How's it going?
Metal from the rock is dissolved into liquid. It is passed through a mass spectrometer capable of spotting tiny metal parts. This incredibly accurate device provides the vital piece of evidence. The blue and red lines show there's 10 times more iridium in the Sudbury rocks than in control samples from normal Earth crust. This is indisputable proof that Sudbury had once been hit by a huge asteroid. But where was the impact crater? The landscape here is flat as far as the eye can see. Scientists believe over millions of years the crater disappeared. Erosion wore it down until all that is left is the faint outline of ring structures seen on satellite images from space. Spray and his colleagues have surveyed the area and found that Sudbury is the second biggest impact site on Earth. 155 miles in diameter. That's 3/4 of the size of the world's largest crater at Vredefort in South Africa. Spray calculated almost 2 billion years ago, a space rock the size of Mount Everest must have crashed into Earth here. When the asteroid hit, it produced an instant crater 20 times deeper than the Grand Canyon.
The energy is so intense, with the shockwave going back up through the projectile, the back flows off, and you end up fragmenting the projectile, the meteorite, such that you may even end up with pieces of the Sudbury projectile on the moon, and that's highly likely. So it actually gets blasted out into space.
But one question remained. Where did the valuable reserves of nickel and copper come from that turned Sudbury into a famous mining site? The asteroid had vaporized, so the large nickel and copper deposits couldn't have come from space. When the asteroid hit, it penetrated almost 18 miles into the Earth, melting a huge cavity into the rock. Scientists estimate that this giant hole lasted only a short while. Within hours, it collapsed because of gravity.
It's just like when you try and dig a hole on the beach in sand. With your shovel, you're spading the sand out, and you can only go so big before the sides actually collapse in.
After the cliffs collapsed, the crater floor filled up with a deep lake of hot, liquid rock. The hole had been created in seconds, but the hot rock took hundreds of thousands of years to cool. During this time, heavier metals like copper and nickel, naturally present in the liquid rock, sank to the bottom and formed Sudbury's deposits of precious minerals. The impact at Sudbury had radically changed the geology of a wide region, concentrating nickel and copper into awesome mining deposits. Impact sites were now more than academic interest. Such rich mineral deposits potentially meant big business and economic wealth. Mining companies on the hunt for precious natural resources now use satellite imagery to reveal new craters around the world. Rings that can be seen from space suggest giant asteroid impacts. They know that these impact sites may contain more than just copper and nickel. Rich gold mines in South Africa were also thought to have been created by volcanic processes. But the discovery of shatter cones in the 1960s and ring structures seen on satellite images revealed what is now thought to be the biggest impact crater on the planet. Here, the impact concentrated valuable minerals in the rock, this time into precious deposits of gold ore. And at Chicxulub, Mexico, scientists discovered traces of a large asteroid impact that wiped out the entire dinosaur population 65 million years ago. But recently, scientists have drawn a link between the massive crater at Chicxulub and a huge oil reservoir discovered nearby. As the asteroid crashed into the Earth's crust, it fractured the underground rock, making it porous. Oil, abundant in the deeper layers below, rose up and seeped into the porous rock, creating an oil reservoir. Now scientists could more easily recognize signs of large impact sites. Shatter cones were evidence of strong shock waves. The presence of the space metal iridium was proof for an asteroid impact. And satellite imagery has shown how impact craters can be linked to vast mineral wealth. Besides the minerals found at different impact sites, asteroids have left evidence of massive destruction. And this has led scientists to a terrifying conclusion. If it has happened in the past, there is little doubt it could happen again. October 9th, 1992, Johnstown, Pennsylvania. Thousands of sports fans were watching their local high school football game when a dazzling meteor slashed through the skies. In only a few seconds, it traveled over eastern Kentucky, North Carolina, Maryland, and New Jersey. It became one of the most filmed fireballs in history. When it landed in Peekskill, New York, it smashed the trunk of a car. Luckily, no one got hurt. November 20th, 2008. An asteroid struck Earth again. A mighty fireball streaked over western Canada. As it dashed through the skies of Alberta, it broke into thousands of little pieces. It is the greatest number of fragments recorded from a single fall. Each year, almost 4,500 small-sized meteorites greater than 2 pounds each hit Earth. Over 99% of the impacts stay unnoticed, and damage is minimal. But on rare occasions, asteroids can be devastating. 13,000 years ago, the great ice sheets were in retreat as the last ice age was coming to an end. The Clovis people, one of the first human inhabitants of North America, roamed the Great Plains alongside giant beasts. A team of archaeologists is investigating the evidence they left in the Sheridan Cave in Ohio, southwest of Lake Erie.
Clovis peoples were hunter-gatherers. In other words, they hunted wild game and they gathered wild plant foods. At this time period, there were animals we call the mega-mammals, which included large elephant-like creatures such as the woolly mammoth, as well as the American mastodon.
Then, suddenly, all evidence of the mega-mammals and the weapons used by the Clovis people disappeared. The same observation was made by geologists at other excavation sites across America. Tankersley is convinced a catastrophe drove the mammoths to extinction.
And it would have happened in a snap of a finger. Over 30 genera of mega-mammals went extinct, and the Clovis technology disappeared forever.
Clues to what happened came from another part of the cave. It's in a geological formation known as the Black Mat Layer. It is a dark line of rock packed with charred debris, and it suggests a violent death.
The black layer, which you see in this profile, is carbon, a high organic content, and what we're seeing is the remains of animals which were living at that time, which literally had the flesh burned off their bones. In order to do that, we're talking about somewhere between 500 and 1,200 degrees Fahrenheit.
The cause of the inferno has long been a mystery. But deep in these Ohio caves, Tankersley thinks he has found traces for an asteroid impact.
This is what's known as a magnetic susceptibility meter. It looks at the degree of magnetism of the layers of the sediments. If we take a reading in the layer that predates the asteroid or comet strike, and we look at the reading, it's somewhere around 7. If we compare that at the Black Mat, where we're finding micrometeorites, we're looking at 50 times the magnetism of the layer before we have evidence of an asteroid or large comet.
Like at Meteor Crater in Arizona, Tankersley believes the asteroid brought in large amounts of iron, causing a strong magnetic field. As the asteroid entered the atmosphere, it burst into thousands of smaller micrometeorites. He believes that the impact annihilated the mega-mammals and brought the Clovis people to the edge of extinction. Skeptics within the scientific community doubt the theory. They think the devastation could have been caused by lightning or a wildfire started by the Clovis people themselves. But recently, further evidence for the destructive power of these killer rocks has been uncovered. In March 1994, Carolyn Shoemaker and a team of astronomers made an extraordinary discovery. They were observing and recording the night sky when a giant fireball approached Jupiter.
Here was this fuzzy bar of light, and I looked at it and thought, what on earth? It looks like a squashed comet, because it was fuzzy.
It wasn't quite an asteroid, but a comet with a tail. Now called Shoemaker-Levy 9, the comet's mixture of giant space rocks and ice was heading directly for planet Jupiter.
Very exciting. We had already been up on a high, and we went up even farther because this was so unusual. No one had ever actually seen a comet in orbit about Jupiter. Although we knew they had been there, no one had seen a comet impact another body in space.
For the first time, the whole world was watching rogue pieces of rock hurtling through space towards a planet. As they entered Jupiter's atmosphere, something incredible happened. The rogue pieces exploded, causing giant shock waves. They left a series of holes in Jupiter, each bigger than the Earth itself.
The impact on Jupiter was sensational. It was very large. You could see the dark spot, and you could see the first ring, and then you could see this cloud of dust.
The team had witnessed an airburst. As the giant fireballs approached Jupiter at high speed, they were slowed down by the planet's atmosphere. The energy of motion was converted into pressure and heat, and resulted in a huge explosion. A similar airburst over Earth would annihilate all life on the planet. Physicist Mark Boslow works at the top-secret Sandia Research Laboratories in New Mexico. He's one of many defense scientists investigating the possibilities of such an Armageddon. Research suggests we might not be as safe as once thought. The investigation leads to a remote region of Siberia. On June 30th, 1908, a bright flash streaked through the skies. Seconds later, the sound of an explosion followed. The area of Tunguska was hit by an airburst. A devastating shockwave uprooted thousands of trees and flattened more than 830 square miles of taiga forest.
There is still some evidence. There are some of these trees that had all their branches stripped off in 1908, and those trees that have been dead now for 100 years are still standing.
Scientists assumed the destruction must have been caused by an asteroid of at least 100 feet. And they also believed asteroids of this size would hit Earth only once every 1,000 years. But in 2008, Boslow discovered something alarming. With advanced computer simulation, he calculated that a small meteorite of only 20 feet across could cause a Tunguska-like event.
The airburst was actually smaller than people have been thinking for the last 20 years or so. And the reason we think it was smaller was because of this neglect of the momentum that continued to carry the energy down. What I'm showing here is an asteroid coming from the upper right, and it's pushing down into the atmosphere, and about 7.5 miles above the surface it explodes. but you can see that it continues to push downwards. So all that energy is continuing to push downwards, and it's driving this shock wave ahead of it. The shock wave is a big blast of air, hurricane force winds. Now that's what blows the trees down.
Based on this theory, asteroids able to cause another Tunguska could statistically hit our planet every 100 years. If such an airburst happened over a populated area, the consequences would be devastating.
Well, if something like this were to hit or explode over the sky of Los Angeles, it would destroy buildings over that same kind of area, 800 square miles or so. So it could completely wipe out a large portion of the Los Angeles metropolitan area.
The investigation has revealed that asteroid strikes can be incredibly destructive. The black mat layer of sediment in the Sheridan Cave in Ohio is evidence that an asteroid impact might have led to the extinction of the mega mammals. An explosion of a giant fireball in Jupiter's atmosphere showed scientists in real time the destructive power of airbursts. And an airburst over Siberia leads to evidence that a meteorite as small as 20 feet across can cause massive devastation. The powerful force of an asteroid is evident, but the story doesn't end here. The actual asteroid rocks, when examined, reveal extraordinary secrets about the beginnings of our solar system. Asteroids plunging from space have transformed the surface of our planet. But there was one thing scientists still had to investigate: the leftover pieces of the asteroid rocks themselves. They contain valuable information about the origins of our solar system and the formation of planet Earth. But this presents geologists with a problem. Most giant asteroids vaporize when they impact Earth, destroying much of their hidden evidence. Geologists had to search for smaller pieces of broken asteroids called meteorites instead. With little weight, these rocks survive the fiery plunge through the Earth's atmosphere and land intact on the planet's surface. Jeff Notkin and his group are hunting meteorites in a dried-up riverbed in Arizona. They are scanning the ground with metal detectors, hoping the signals they are getting lead them to iron meteorites. For the most part, they find iron dust, small magnetic particles from space, which stick to the magnetic hammer.
The estimate is thousands of tons of meteorites fall on the Earth every year, but most of those, the vast majority, are tiny dust-sized particles that collect over the surface of the Earth and are never noticed.
What Notkin is really seeking is not space dust, but extremely valuable pieces of rock from outer space. He has been hunting meteorites for over 15 years and has built up a collection of over several hundred samples.
There are three basic types of meteorites. The irons, which are my favorite, which are what most people imagine a meteorite really looks like. And they frequently have very attractive aesthetic surface features like this piece caused by melting in the atmosphere. The next group are stones, and these are fairly similar to, at least in appearance, to terrestrial rocks, although they contain chondrules and iron and nickel from outer space, which we don't find in Earth rocks. And the third group, the stony irons, is the rarest of the three and also the most valuable, and the value on something like this would be at least $25,000 to $30,000. And if we were to take this piece and cut it open, we would reveal this beautiful interior, olivine crystals, and they're known popularly as the semi-precious gemstone peridot.
Monetary value aside, to geologists like Minnie Wadwa, these meteorites are a window into the Earth's ancient past. At Arizona State University, she runs a department analyzing some of the oldest meteorite rocks that landed on Earth.
This meteorite right here, this carbon-rich chondrite, this probably is a close proxy of the kinds of materials that were bombarding the early Earth. And they're called chondrites because they've got these tiny little inclusions, spherical inclusions in them called chondrules, which are amongst some of the earliest solids that formed in our solar system.
In the beginnings of our solar system, there was nothing but gas and dust. As it cooled, solid asteroid rocks began to form. With modern technology, scientists have been able to pinpoint their exact age.
Most meteorites are thought to have formed 4.6 billion years ago, but modern techniques have now made it possible for us to actually age date meteorites with much greater precision. And we now know by looking at meteorites like this one, for example, that in fact the solar system was formed 4.567 billion years ago. And we know that date within a million years or so. So essentially we can very precisely age date the formation of our solar system by looking at meteorites.
As the meteorite rocks floated in early space, they collided and grew into bigger bodies. These ancient rocks were the building blocks of planets, including early Earth.
By looking at these types of meteorites, we can actually begin to understand how our own Earth might have formed and what kinds of processes might have happened on the early Earth, because we actually get to look at the deep interiors of small planetary bodies when we're actually looking at some of these meteorites.
After the planets formed, the rubble which was left accumulated and formed a cloud of dust and rock between Mars and Jupiter. This is called the asteroid belt. Every now and then, one of these rocks breaks free and tumbles through space at 25,000 miles an hour. When it drops through the atmosphere and lands, it delivers priceless information about conditions on the early Earth. Perhaps even hints as to how life itself began. In the late 1960s, a remarkable fall of meteorites hit the town of Murchison in Australia. Scientists around the world took notice.
Well, basically it consists of silicate minerals, very much the same.
Hundreds of pieces fell from space, greeting the residents of Murchison with a pungent smell of rotting organic material.
If you open up this jar of closed Murchison and smell it, it actually smells very strongly of sort of volatile organic rich compounds that are being degassed from this particular rock even today.
Professor Wadhwa and her department began analyzing the Murchison meteorite. Incredibly, they found it contained organic compounds called amino acids. These complex molecules are essential to all life.
The organic materials in this type of meteorite were actually the building blocks of life as we know it today. This is the raw material from which life began on our own planet.
It's possible that the seeds of life arrived from space, flown in by asteroids and meteorites.
In the case of our own origins, it's not absolutely clear that we need have necessarily originated on Earth. The seeds of our life and the very primitive life forms could have actually come from another planet or even another solar system.
New insights into asteroid impacts has revolutionized our understanding of how the Earth was made. Overturned rock beds around Meteor Crater were clues for a massive impact. Advanced computer modeling shows how asteroid rocks are vaporized after impact. Traces of iridium in the rocks in Sudbury were evidence for an asteroid impact that concentrated precious metals. From meteorites landing on Earth, scientists were able to calculate that our solar system formed exactly 4.567 billion years ago. And the analysis of these space rocks showed that the organic seeds of life had perhaps arrived on Earth, flown in from space. Asteroid impacts profoundly shaped the geology of our Earth. But as examples from the past have shown, they have the power to annihilate our entire planet in an instant.